All right, so let's now look at an additional example about how we can calculate the volume of a solid by accumulating the slide volumes. So this is an additional example aside from my general video lecture about the slides method for calculating volume. So in that way, it is required that anyone viewing this video lesson, this video example, must view the general discussion lecture before viewing this particular lecture. And in addition to that, it is highly recommended to watch this content here after you have learned and understood to what the fundamental theorem of calculus is. So in that way, find my lecture about my video lecture about the fundamental theorem of calculus to also know what that is, in order to understand well the later content of this video lecture over here. All right, so let's look at the wording description of the problem on my computer screen here. All right, so here we're looking at another solid right here. So here the problem gets straightforward into asking us to find the volume of a solid where, and so now this object here is having the following description. So just like how I have been explaining in the general discussion lecture, then there are always two descriptions. Anytime we're doing these problems, there are two descriptions. One description is about the base region. So the solid here has the base being a semicircle of radius 1. All right, and then after understanding the picture of the base region, then we move on to the description of each slice or each stripe here. So each cross section, and so again from the understanding that we've got out of the general discussion lecture, then a cross section came out from each stripe here throughout the region, throughout the base region. Here we draw stripes that is perpendicular to some axis, and so but though in the end those stripes are parallel to each other. And we erect the cross sections over those stripes again. So now this part right here describes the stripes, the cross sections that came out from the stripes. So each cross section perpendicular to the diameter edge, okay, is an isosceles triangle, an isosceles right triangle where the right angle is on the circle. Okay, so it's a lot of fancy description right here, but let's first have a look at what that picture, what it looks like to be in the base region here first. So right now I am going to look at the base region. So this is what the base region looks like. Okay, and so at this point, let's not be too worried about the axes or whatsoever. But now here's in a 3D, here's how I put on the stripes right here. All right, so with the region being a semicircle, and this is the radius here being 1, and so the stripes are like that. The stripes being perpendicular to some axis. Actually, the description here was saying the stripes, the cross section perpendicular to the diameter, to each cross section perpendicular to the diameter edge. Okay, so that means on the picture here, again, just like how I was explaining, each cross section came from a stripe. So on each stripe here, then we can build some kind of a shape over that. And so now, according to the description, then each cross section being perpendicular to the great chord. Okay, and right now, again, just like I said earlier, we don't need to worry about what axis this is. Okay, and the program I'm using for this picture right here has some label f of x with g of x, but I don't need any one of my viewers to worry about these. Those are just there for dummy reason, and sadly I don't know how to turn that off for now at this moment. Okay, but so these are the stripes. They are perpendicular to the diameter. And so now, based on the description, so we have now understood and seen well the shape of the base region. And now let's look at what the cross section really looked like. So the description here says each cross section perpendicular to diameter is an isosceles right triangle. Isosceles right triangle. And there's a little further description right here where the right angle is on the circle. The right angle is on the circle. Okay, so now let me turn back over to the actual 3D picture right here so that I can show what it means by each cross section. So over the stripe we built the isosceles right triangle, but then there's a further description, detailed description here that says the right angle is on the circle. The right angle is on the circle. So what it means is that this is the diameter and the circle side is here. So we have a right isosceles triangle. So now let me rotate this. All right, so there we go. So these are over the stripes right there. We built the isosceles right triangle. So let me turn to a different angle so that you can all see. All right, so these are the right triangle. The circle side is on this side. And so the right angle side is on the circle. And that's what it means by, each cross section. You can still see these are the cross section right here. Some cross section is smaller than the other cross section, but that's what it means by each cross section is an isosceles right triangle where the right angle is on the circle side right there. Okay, and so I brought up this problem in the intention that to make it really consistent with what I taught in the general discussion lecture, that here a solid is just a solid. And I don't want anyone to be worried about, is that the x-axis or the y-axis? That's not the point. Okay, and so now let me make the sketch of the base region on the board here. All right, and then we are going to have some understanding over that. Okay, so just like that, now you have seen with the computer animation. So now allow me to put this is our semicircle. All right, and allow me to draw that in sort of like a 3D perspective right here. So all I know is that each stripe being perpendicular to the diameter here. Okay, and this is not even the middle stripe. There we have a lot of stripes throughout here, and the stripe's length varies. And so in that way, in the way how it looks right there, then the right angle comes out like that. The right triangle comes out like that. Okay, that's what it looks like. But isosceles right triangle means it's a triangle where it's a 45, it's a 90, 45 triangle right there. Okay, so that's what it is. And right angle is on this edge. Right angle is on this edge. So we can have so many cross sections like that, or so many slices like that in the terminology that I was using in the general discussion lecture over here. And all we know is that this diameter here, on this great chord right here, our circle has radius 1. Our circle has radius 1. That's everything we know about our base region. And then again, we erected on top of our base region those triangle. And that's why, so now in this case right here, yes, just like that fundamental when we're about to calculate the volume, each slice here has an area. Each cross section here erected right above our stripe has an area. So I'm going to refer to that as a slice to be consistent with what I have been teaching in the general discussion lecture. So slice is area, or the area in each slice I am going to multiply with thickness. Okay? And so just like that, it may be hard to see it in my picture, but the thickness, see, that's how thick my pencil stroke is. That's the thickness of each cross section. So there we have a thickness. Okay? We have a thickness. And then we multiply that thickness with the slice area. That's how we get the volume of one slice. The volume of one slice. And then we are accumulating. We're accumulating from some starting point to some ending point. And that's how it's, this is, how it reflects the general, that general fundamental that I was introducing in the general discussion lecture right there. That's everything we need. And an integral we're about to use to apply to find volume in a problem is accumulation. Okay, and so now I eventually will have to erase some of these extra notes here so that I can make other notes in this picture of mine. But so let me once again turn over to the computer the graphical solid on the computer so that you can see. So that we have, so with these slices here, see we have, each slice has its own thickness, okay? And then with each slice having thickness right there, each slice has its own area on the cross section, okay? And that's why multiplying the area of each slice with its thickness right there, we have the volume of one slice. And then we're accumulating all the slice volumes from the beginning, from some start to some end. That's how we get the total volume. So now let's even dive in further. So like I said, this problem here, we're starting out completely from scratch with a figure that has nothing to do with x-axis or y-axis or even u-axis or t-axis whatsoever. We have our own control over that as long as we understand where the base region come out from. And then throughout the base region we drew, so there was a description about the stripes. So the stripes were were required to be perpendicular to that diameter of the base region. That's all we need. And then on top of the stripe, over the stripe, we erected those isosceles right triangles like that. So just like how I was explaining in my general discussion lecture, that we always start out with the base region, and then in a way how we shading in, we create those stripes, and those stripes are the parallel stripes. See, in here the stripes are parallel because in the sense that they're all perpendicular to this the diameter chord right here. See, all the stripes are supposedly parallel. It's just the way it is, Euclidean geometry. Okay, and so now in that way, we're gonna put the axis on. And so having the axis on is just a tool so that to keep the calculation going for us. And so at this point right here, we have our own control to put the axis. The point now is that we always want to put the axis in a way that it's perpendicular with all of the stripes. That's what I explained in the general discussion lecture right there. So the point now is that we always gonna put the axis, the main axis. Okay, there's always the horizontal axis or the vertical axis. You can put it any way you want, but the major axis, there's only one most important axis. And that you always need to focus. You can see that when I was doing that in a general discussion lecture, I mainly only need one axis. We put that axis to be perpendicular with all stripes here. So my stripes are already perpendicular to the diameter in this base region. So it's better that we put our axes, here, our main major calculation axis, parallel to the diameter here. Okay, but then why not putting it away too far from this diameter itself? Just saying, so the main requirement, this axis has to be perpendicular to all stripes. But then in the end, why does it have to be this far away from the major chord, from this great chord right here, this diameter? Because there was no restriction that we have to put the axis away from the region. So it's even easier as a matter of fact. So now as a matter of fact that I realize, it's even easier that we put the axis right here. Right on that. We put the axis right on that diameter, or a lot of time we call that it's a great chord. Okay, so that's one thing making it easier. And furthermore, if we have a vertical axis, so think about this is the horizontal axis. If we have a vertical axis, why not putting this circle, this at least is a semicircle, but why not putting it right at the origin, meaning the other axis going out this way? Okay, so right at the origin. So this is the other axis. That's the other axis. And so here's the thing. I just want to really emphasize the fact that this is the major axis that we use for the calculation. But whatever the axis name, it should not matter. You can call this the x-axis. You can call this major axis the y-axis or the t-axis or the u-axis. Let's call it the u-axis. I purposely want to stay away from the usual the naming convention so that you can understand our main goal is to get the volume here, but not to be worried about the volume in the end. Will not be dependent on the name of the axis we're putting here at all. So, you know, if I keep putting that x here, then eventually some viewers, some students of mine will be tied down to that. Everything has to be on the x-axis. Nope. the point is there's a major axis that we do the calculation on. And from that major axis, now here if I call it a U, and again in our understanding, then I said why not putting that center of the circle right at the origins where this major axis cross with another vertical axis. So this vertical axis, you can call that it's a y-axis. Who knows? Whatever name that is. U and Y, okay? But the y-axis here is not important. This u-axis here is the major axis. All right, because in the end, our ultimate goal is just to get the volume of this solid right here, the volume of this solid that we are seeing in the picture here. Okay, so the program I'm using here is still using the x variable, but like I said, that shouldn't be the factor that anyone need to pay attention to. And as a matter of fact, I wanted to disable that, but I just haven't found out a way. The software here is relatively a little bit new to me. Okay, but anyway, so this is the major axis. So now in our problem, I call that this is the u-axis. It's the u-axis, and this is the y-axis right here. Okay, and so now back in the problem itself. So in the way how we reference our base region to that major axis, this is where once we have that major axis, then every calculation is going to be relative to that variable's name. We name this ourselves as well. All right, so now in that way, the thickness, okay, it is apparently now clear that the thickness has to be relative to this now named axis, and the thickness is that du expression. The thickness is the infinitesimally small change in u variable. All right, and so in the way how I was putting up with the vertical axis, the origin between these two axes here, and how that is aligned with the center of the circle, then this point right here has to be u equals 0 right at that origin. Okay, and so now, but anyway, so thickness just now is found in the way it is. Makes sense to be du. So just like that, my first step, personally recommended, is to identify thickness of our each stripe, which consequently becomes each section. So thickness of each cross section in the picture that I placed like this is called a du. Okay, if you see a problem like this being taught in a textbook, they might call it dx, they might call it a dv, they might call it a dy, whatsoever. The point is there's a major axis. Again, I have to emphasize that. All right, and so now once we identify our thickness, then I can, so similar to how I have been doing that in the general discussion lecture, then I am going to partially fill this expression into my fundamental here, into my general fundamental as a fundamental formula to calculate the volume by slicing right there. So thickness now is du. Okay, and then so now what we're still waiting ahead here is to come up with, what's still waiting ahead for us here is to come up with the slice area, the area on each slice, and then it's going to be accumulation from some start to some end. That's how things happen. But now once we've had that decision, once we have realized our thickness here is being a du in the way how we define our major axis here, then the slice area, have a little bit of expectation for yourself. Even we didn't get to there yet, but the slice area, the area of each slice, eventually will have to be in terms of u. That's, and I'm really making it consistent with the way how I have been teaching throughout all my other or in earlier video lessons about the concept of integral. Okay, so if we decide the d expression here to be a u, the du, then the function here eventually that we derive has to be a function in terms of u. Okay, so now in that way, let's have a look, a closer look, to have a clear picture, to come up with a plan to calculate our area of each slice right here. All right, I'm going to navigate over to the other board and let's do some quick scratch work. So now if we're looking directly at the u-axis, think about, we place our eyes straight into that, then the semicircle is looking like this, and as I said, we did this on purpose. We put our center of the semicircle, because the semicircle came out from a circle, so we put the center of the circle right at the origin between this u-axis and some other vertical axis. So this point right here is a 0, 0. Okay, that point right there is a 0, 0. So in that way, if anyone, well, let's name that, maybe it's a y. Okay, so famous equation of any circle. Famous equation of any circle is a u squared plus y squared equals, now this circle is known from the description of the problem, known to have radius 1. Okay, so the radius here is 1. So that means this circle has to have equation u squared plus y squared equals 1 squared, which is 1. And then for anyone viewing this video, if you are surprised about this equation that I came up here, make sure you review your algebra right here. But allow me to not to go back, not to go too far back into the algebra over here. Okay, but so the equation of any circle, and this is the special equation for the circle that's always centered at the origin. Okay, u squared plus y squared equals 1. And so from that way, we have our choice, because you can see now each stripe is placed at a u value. Okay, and so the length of each stripe varies, depends on where we put our stripe. So if we put our stripe at a u value somewhere here, then the stripe, and then the length is shorter. And then when we put our stripe, let's say right at u equals 0, then we have looks like the highest stripe right here, the longest stripe, and then the stripe gets shorter and shorter again. It's all changing. Okay, so as a matter of fact, let me swing back to the computer station and then show you how the stripe looks like, how the stripes are changing, how each stripe is changing length as we are going from into different u variable over here. So this is our u-axis, okay, instead of the usual x-axis, and this is the y-axis. We name these axes ourselves right here. So if we have a stripe about here, see, it's some length, and then we move to the stripe to a different u value. It's a different length, higher, okay, and then we're moving it back down here. It's a different length. But in the end, the point I'm trying to make now is that the length of each stripe looks like, in a way, how we're placing our picture, in a way how we decided to place our picture. Each length here appears to be the output value of this function as a function of the u variable. Okay, so again, I'm repeating, it looks like, in a way, how we placed our circle. Then the length of each stripe here has to be the function output. If we can express this function as some function in terms of u, if we can express this circle right here, this semicircle, this curve right here, as a function of u, and so the access to that, the access to expressing the height of any stripe as a function of u here is from this equation. So it's actually a quite easy algebra work right here. I'm going to subtract u squared from both sides. That gives me y squared equals 1 minus u squared. I'm getting closer. Okay, and then I'm going to solve for y. The y variable is going in the vertical axis. The horizontal, the u variable is going on the horizontal axis right here. So now I want the function here, the height here, is represented as a function output of a function in terms of u. So that's why I'm solving for y in terms of u out of this equation. Okay, and so now I'm going to take square root of both sides. And again, I have to yell it out loud. Anytime we're taking square root of both sides, we need plus and minus square root of 1 minus u squared. Okay, plus and minus 1 square root u squared, meaning solving this for y, we end up with two expressions. One of them is a positive square root expression of 1 minus u squared. The other one is a negative square root expression of 1 minus u squared. Which one here is appropriate for that one? That's our decision to make in the next step. So now, which one here is the appropriate expression for that curve? Now it looks like, in a way, so everything here is everything here that we're moving here, every step that we're moving here is directly coming out from what we decided earlier to place our picture like this. Okay, so in a way, how we place our picture like this, then it's a positive, because see, it's a positive y value up here. Instead of the down bottom semicircle here, we place our circle in the upper part. Okay? So that's why in that way we actually chose. Now we decided the function output that we use here the function here is a positive square root 1 minus u squared. That's our function to determine the height or the length of each stripe that produces our cross sections. Okay, and so now in that way we got so any of the stripe here has length determined by the u variable here, by the value of u, positive square root of 1 minus u squared. Now we know a way to determine the length of any stripe. And so now things keep getting better and better for us. Allow me to erase this, and you can always roll back on this video to see how I derive that function output. But anyway, so now we know at any u value, then our length of the stripe is a square root of 1 minus u squared. And then we're going to put the triangle, see, just like back in this picture right here. So maybe it's also a good idea that I make notation right here. So this stripe length right here is expressed as a square root of 1 minus u squared. Okay, and so, but it's a right isosceles triangle. So over each stripe we're going to erect a right isosceles triangle where, according to the description, the right angle is on the circle side. That's why I drew it like that. But notice the way how it is, being an isosceles right triangle, this edge right here has to be equal to that edge. So that means this edge right here that I'm pointing the arrow to is also, if this edge here is determined as square root of 1 minus u squared, then that other leg right here is also square root of 1 minus u squared. Okay, 1 minus u squared. Because it's an isosceles triangle, and now being a right triangle, that height right here is also acting as the height of our triangle. So now area of a triangle, area of any triangle. Now we all certain feel that we are ready for getting the area of each slice being a triangle, being an isosceles right triangle. Okay, slice area. All right, so here we go. Base being a square root of 1 minus u squared times height, which is exactly the same expression. So that's why we have square root of 1 minus u squared all squared. Base times height, which is in this squared expression, multiplied with 1/2. So now it's a 1/2 in parentheses square root of 1 minus u squared all squared. All right, so now that is our expression representing the area of any slice here at generally a u variable, at any u value. Okay, and let's check for a consistent, let's look at this as a checkpoint for consistent right here, but our slice area is expressed in terms of u. That's making it consistent with the fact that we have already decided our thickness is a d expression being a d du. Okay, and so now we are ready. I'm going to fill in with this slice area as this is a 1/2 square root of 1 minus u squared, but I'm going to allow me to erase this extra parentheses here, but that needs to be squared here. All right, that needs to be squared here. And so now the last thing to do now is to decide for us where the start and where the end of this accumulation here. And the accumulation here depends on where the base region starts. So it looks like in this circle the base region starts from that left end and ending at this right end. And our region, our base region, our circle, in this picture on my other board has the equation. So the equation here is this, or we can also look back at that a little bit. It's u squared plus y squared equals 1. Okay, radius 1. So the left, the very far left here has to be, this is u equals -1. And then this last one this very last one on the right hand side, right hand right here is u equals +1. It's the way how it is with any of the circle. Okay, and there are so many ways to verify what I'm doing here. So allow me to just mention it without a solid verification of that. But again, what I'm saying here is the starting end where this curve crosses with the u-axis is at u equals -1. The right end right here is where the graph crosses with that u-axis again is at u equals 1. This is the end of our accumulation. All of the stripes are accumulated from from u equals -1 to u equal 1. Okay, And so in that way, we are ready to complete our integral. The start of the accumulation is at is from -1, and the end of our accumulation is at 1. So now, ladies and gentlemen, we have come up to a successful, complete integral setup of our to calculate the volume of that solid right here, the volume of this solid that we are calculating. All right, so the volume of this solid can be calculated by, and based on the description of that solid, okay, then the volume will be whatever comes out after we evaluate this definite integral. Okay, and so at this point, once we have successfully completed our integral setup to calculate it, this is where we need to use the fundamental theorem of calculus to make the work easy and go on the fly right there. Okay, and so that's the reason why I said earlier it is highly recommended to view this lesson here, to view this particular example, a video example here, after you have already learned what the fundamental theorem of calculus is. So you can always pause the video here and open my earlier video lecture about when I taught about the fundamental theorem of calculus. Because usually any of these videos must be taught and given after I have taught about, after I have delivered or posted my other videos about the fundamental theorem of calculus. Okay, and so now allow me to erase this extra information here. We are ready for using the fundamental theorem of calculus to evaluate this. All right, so the volume here at start is an integral from -1 to 1. It's a 1/2, okay, square root of 1 minus u squared with r squared with a du. It's an integral. Whatever variable here shouldn't change the final answer. Okay. The square here algebraically will cancel with that square root, so that's making the problem even easier. So that now, and so I'm just working with the algebra before I'm getting on with that actual fundamental theorem of calculus. So here, I see the square will cancel with the square root, and the 1/2 here can be placed in front as a coefficient. So here I'm putting the 1/2 here, and then there's an integral from -1 to 1, 1 minus u squared du, and the problem shockingly becomes even more and more, even more and simpler. Okay, and so now it's a very simple integral right here, and you can even take advantage. To the fact that, and we can observe that this is a symmetric interval of integration, and then the function itself right here is an even function actually. So we can take advantage of that, and because I also had a lecture about how we can take advantage of that optionally if we recognize. If you don't recognize it is just fine that we're doing a 1/2, and now take the antiderivative u minus the 1/3 u squared. That's the antiderivative, and we keep everything exactly the same, and we do the evaluation from -1 to 1. This is for anyone who does not recognize the evenness, okay, of this function right here, the odd and even property of this function. But now allow me to point out that because doing this is still going to get you to the correct answer, but that's taking a little longer time. So I would suggest to see this function here, the 1 minus u squared, as an even function, because it is. And then this interval itself is being quite a symmetric interval. And so I'm going to do the following. One more algebra treatment step right here. It's going to be I'm going to turn that into a 2 times. Okay, the actual integral is a 1/2, but 2 times the 1/2, and then now I'm only going to move on. I'm only going to proceed the integral. So 2 times, it's a 1/2, but the integral is only happening from 0 to 1. 0 instead of -1. We're only going halfway, and then we double that integral calculation. Okay, and then 1 minus u squared with all that du. All right, and so now with this integral, I have a little bit of advantage. I can cancel away that coefficient. So 2 cancel with 1/2. And so now really at this point, the integral we're looking at that we have generated is simply an integral 0 to 1. It's 1 minus u squared du, and this integral is even easier to handle. So I do the problem, and I have to give a lot of explanation. So that's why it seems like it's a lot of time looking through, but these steps, when you're actually doing that on your own, it takes a much less amount of time. And so now the antiderivative steps is here. u minus 1/3 u cubed, and that's all we need. We no longer need the 1/2. We only need to evaluate this antiderivative from 0 to 1. From 0 to 1. Okay, and then from that way right here, it's even more advantage that we can just simply do the substitution of 1 into each variable here. So 1 minus 1/3, okay, cube. And then surprisingly and shockingly, I don't even need to swing to my other board right there, because all of that 0 here substituting there is simply a 0. All right, all of that there is just a 0. So now in this way right here, I don't even need to swing by my computer station to grab an answer. This calculation is simple enough for anyone. So 1 subtracted 1/3. Okay, and we don't have to worry about any of that at all. So 1 subtracted 1/3, our final answer is simply going to be a positive 2/3. And that is the final answer to how big that volume is. Our final volume. Our volume of this solid here is 2/3. Okay. All right, so I mentioned this throughout the steps I was explaining already, but the specialty of this problem is that it's emphasized what I taught in the general discussion lecture, that a lot of time we actually start out with an object, with a solid that's not really having anything to do with the x-axis or the y-axis. We just simply need to focus straight on what I taught fundamentally, that we have a base area, being whatever shape that is described in the problem. We have a base area, and then through the base area we have parallel stripes. And so in this requirement, all of those parallel stripes are perpendicular to the diameter here, or the great chord right there. Then we purposely place, we always gonna place, once we identify the base region and identify out the characteristics of our stripes, we always gonna put some major axis to be perpendicular with all stripes, so that it starts, giving us a way to do the calculation. So putting the stripes here, putting the axis here is completely on our own control right here, just like how I explained in the general discussion lecture, so that no one have to worry about, where's the x-axis, where's the y-axis, or whatever you can call it the y-axis here, you can call it the u-axis here, you can call that the x-axis, the t-axis, whatever, but it's a major axis where all of our variable eventually become just one variable expressed in terms of whatever axis we placed there. Okay, and that's how we come up with this final answer.